Okay, we're going to take a look at our two additional lessons here, starting with lesson 13. Similar to what we did in Unit 2, where we did a couple lessons on Pythagorean Theorem, we're going to look at another proof of the Pythagorean Theorem, not the informal proof, but because now we have some information about similarity, we can use this to do another proof of the Pythagorean Theorem. So, the concept of similarity can be used to prove one of the greatest theorems in mathematics, the Pythagorean Theorem. What do you recall about the Pythagorean Theorem from our previous work? Well, it's about the lengths of the legs of a hypotenuse of right triangles. Specifically, if A and B are legs of the right triangle and C is a hypotenuse, then A squared plus B squared is C squared. The hypotenuse is the longest side of the triangle and it is opposite the right angle. So what we are going to do in this lesson is take a right triangle, triangle ABC, and use what we know about similarity of triangles to prove that A prime plus B prime, A squared plus B squared equals C squared. So in your math journal, we're going to go ahead and sketch out this proof. Go ahead and sketch the triangle using a ruler. It's important that we have straight lines when we do this. So just write a medium-sized right triangle, A, B, and C, with C being the right angle, and label the legs accordingly to where small a, small b, and small c are opposite the angles. So for the proof, we will draw a line from the vertex C to a point D so that the line is perpendicular to side AB. Now don't worry about it being exact, but it should look something like this. It's just we will indicate that where this line intersects line AB is going to be a right angle, even though it might not specifically be, but you should try to draw it to where it looks like it should be. So draw this particular line CD, because we draw this because it divides the original triangle into three similar triangles. Now you might be saying, well, wait a minute, that's a typo. There's only two triangles. But don't forget, we have the original large triangle too. So we actually have the whole thing. We have a smaller one here and then a medium size here. So we do have three similar triangles. Before we move on, can you name the three triangles? Well, the three triangles are ABC, ACD, and BCD. So let's look at the triangles in a different orientation in order to see why they are similar. We can use our basic rigid motions to separate the three triangles. Doing so ensures that the lengths of the segments and degrees of angles are preserved. So when we watch the video later on in this lesson, you will see how we can use the transformations to move these so that they are separated out and in the same orientation. But basically we've taken those two triangles and moved them away from the original so that they are all facing the same way. So in order to have similar triangles, they must have two common angles, and by the AA criterion, which angles prove that ACB and ADC are similar? Well, it is true that ACB is similar to ADC because they each have a right angle and they share angle A. So we don't have to do any figuring. We can just look that these two share an angle A, which should be the same because of our transformation, preserves angle degrees, and also C is the same. So since we have two angles that are the same, that means that these two triangles are similar. So what must that mean about angle C from ADC and angle B from ACB? Well, it means that the angles correspond and must be equal in measure because of the triangle sum theorem. So which angles prove that ACB and ADB are similar? Well, it is true that these are similar because they each have a right angle and they share angle B. And what must that mean about angle A from ACB and angle C from CDB? Well, these angles correspond and must be equal in measure because of the triangle sum theorem. So if triangle ACB is similar to ADC, and if triangle, that original ACB, is similar to CDB, and notice I color coordinated them, is it true that ADC is similar to CDB, and how do you know? Well, yes, because similarity is a transitive relation. So we have gone from one triangle to another, and from that original triangle to a third triangle, which means this second triangle should be similar, or is similar, to the third triangle. So when we have similar triangles, we know that their side lengths are proportional. Therefore, if we consider triangle ADC and ACB, we can write that the length of AC is similar to the length of AB, and that the length of AD is similar to the length of AC. So by the cross multiplication algorithm, to make similar or equivalent fractions, if you want to say that, that means that when we cross multiply this, we're going to get two of these, or not two of them, but since they're being multiplied by themselves, that is a square. So we have an exponential term here because AC times AC is AC squared. And then we have just the regular AB times AD, which is shown here. So by considering the triangle ACB and CDB, we can write that BA is similar to BC and BC is similar to BD. Same thing. So when we multiply these again using our cross multiplication, again we have another occurrence of an exponent because BC times BC is BC squared, and then again by cross multiplying we have BA times BD. So if we add these two equations together, we will get that AC squared plus BC squared is equal to these two expressions added together. So by the distributive property, we can rewrite the right side of the equation because there is a common factor of the length of AB, which is right here. It's turned around, AB and BA, but again, we're not worried about beginning and ending points, so really this segment is the same as this segment. We now have AC squared plus BC squared is equal to AB times the length of AD plus BD. So keeping our goal in mind, we want to prove that A squared plus B squared equals C squared. So let's see how close we are. Using our diagram where the three triangles are within one, what side lengths are represented by AC squared and BC squared? Well, that would be A squared and B squared, because here's AC, which is the same as B, and here is CB or BC, which is the side length of A. So we have now A squared plus B squared. So there and there. So now let's examine the right side of our equation. The factor AB, or length of AB, multiplied by AD plus BD. We want this to be equal to C squared. So, does it? Well, if we add the lengths of AD and BD, we get the entire length of AB. Therefore, we have, if we multiply this out, AB times AB, which is AB squared, and that is also our C squared. So we have just proven the Pythagorean theorem using what we learned about similarity. At this point, we have seen the proof of the theorem in terms of congruence and now in similarity. So here's just a video to recap what we just did. So I will go ahead and play this, and you can see that everything we just took notes on should fall right in line with this video. Well, maybe not. Anyways, if you copy this down, you can go ahead, or if you write it down later on and look at it, you will see the video for the same proof that we just did. So for exercise 1, go ahead and complete that on your lesson worksheet, then continue the video to check your answer. Alright, so here is A and B. Again, just using our information, we're just doing some applications. So it's just a matter of plugging in the information that we know to figure out the missing side. Go ahead and do exercise 2 on your lesson worksheet, then continue the video to check your answer. Okay, for exercise 2, determine the length of B in the side. And we've been given easy numbers so that they, when we find the square root of 9, we can easily get a perfect square. And here is part B. Alright, for exercise 3, this is a little different. You're going to have to do some work based on what we just did in the proof. So you have to solve the Pythagorean theorem twice for each smaller triangle, because the large triangle is not a right triangle. Then you're going to use that information to find the side of QS. So go ahead and try this and then continue the video to check your answer. So this is what you should have. Again, you have a smaller triangle and a smaller triangle, because if this is a right angle, then this has to be a right angle. So both of these are right angle triangles. But if you notice the large triangle, this is not a right triangle. So we can use the fact that we can make right triangles out of a larger triangle and find a missing side length. So in this case, if we know 17 and 15, we can find this side length, and we know 15 and 25, so we can find this side length, and then we just add them together. So your answer to this would be 28. Alright, so we have now seen another proof of the Pythagorean theorem, but this time we used what we knew about similarity, specifically similar triangles. We practiced using the Pythagorean theorem to find unknown lengths of right triangles. All right, we'll see you in class.